So just to summarize the last time, because anyway we'll need to discuss the rest of the discussion. To summarize, so we obtained the confluent hypergeometric equation by basically collapsing two of the points. Because in the hypergeometric equation we had three regular singular points, z1, z2, and z3. That was in the hypergeometric case. What we did was we collapsed, say, two of these points. Like one of the points I just call it 0, so this is 0. But these 2 points I collapsed, right? So, and to infinity. So z2 and z3 went to infinity, but at different rates. Because if it went to the same rate, then a lot of terms would just vanish and it would become trivial equation. So we had to take both of them going to infinity, but at different rates. So it was something like, I think, z2 was equal to z2, z3. Okay, we just chose 2, z3, and they were going to infinity. So, and with that, what we found was that the equation we got was, this equation, yeah. The resulting equation was simply z d2 by dz2 plus c minus z. In that process, we had to also, because here also there were these parameters, a, b, and c, 3 parameters. So in this limit, in order to get again some useful equation, we also needed to take b to infinity. So basically b is disappeared. So there's only parameters left over a and c. Right? So you get here c minus z d by dz minus au equal to 0. So this was the equation. And the important point about this equation was that, okay, if you divide by z, we see that this function p has a first order pole, the coefficient c, right? And this one doesn't have a second order pole, it is only first order pole. So certainly it's a regular singular point at z equal to 0. However, at z equal to infinity, when we made this, when we transformed from z to 1 over z prime, we saw that at infinity it was an irregular singular point. Okay. Then, of course, given the fact that this equation is just coming from by taking a certain limit of the hypergeometric equation, you would expect also that the solutions of this equation one should be able to write as some suitable limits of the hypergeometric functions, right? And indeed, we saw that the limit was, the solution was, yeah. So there are two roots here. I mean, before I go into that, near z equal to 0, the indicial equations had two roots. The two roots were, say, r1 equal to 0 and r2 was equal to 1 minus c. Right? The two roots were there. I mean, these were the same roots for the hypergeometric equation at z equal to z1, which is 0. Right? That didn't change because, after all, we kept the z1 the same. We just moved z2 and z3 to infinity. So you don't expect these roots to change, which indeed you can explicitly check that these roots do not change. So this implies there is at least one analytic solution near z equal to 0, and that analytic solution, so this implies there exists an analytic solution and which we denoted by phi a c z, right? Just like in the hypergeometric case, there was one analytic solution near z equal to 0, and that is what we called f a b c z. In the same way, here also there will be, so this is just a symbol notation. And then we saw that this was actually obtained in terms of hypergeometric function by this limit f a b c z over b, and then take the limit b goes to infinity. So this is not surprising, as I said, because this equation is coming from there, from this equation, which is hypergeometric. This is a hypergeometric situation. And then from there, we just took some limit where we have to take b also to infinity. So you see that you get this relation. I mean, again, you can check explicitly. All these statements you can check explicitly by looking at you have a series solution there, you have a series solution here, and you can check that by taking this limit, you indeed will produce that. Okay, so that was one thing. Now, these solutions we saw, okay, of course, this is only one solution. There will be another solution also, right, which will behave like z to the power of 1 minus c near z equal to 0, right? And that solution, so the second solution, again, let's assume that this is not an integer. 1 minus c is not an integer. Then the second solution will go like z to the 1 minus c. And once again, you can just do the same thing that we were doing before for the hypergeometric. You write the second solution as this times some analytic function f of z, right? Substitute that back here, and you will find a differential equation for f. And that differential equation again turn out to be the same form, except this a and c will change, right? And you find from that you can read off what it is. This should be again given by this phi, because this is analytic, but just a and c will change. And you find, by working out that, you find that second solution is phi, this power times z to the 1 minus c times phi a minus c plus 1 comma 2 minus c z. Okay. So these are the two solutions. Of course, any solution, any linear combination of this is also a solution to that equation. Now, the important point was that both of these solutions, by the way, you see that here, going back here, there are only two singularities in this for this equation, z equal to 0 and z equal to infinity, right? At z equal to infinity, of course, irregular, but at z equal to 0 is regular singularity. So both of these solutions, you can write down the series expansion near z equal to 0, and that series will be convergent in the entire plane. Because you see, the radius of convergence is the nearest, the circle whose distance is the distance to the nearest singularity. But the nearest singularity is infinity, right? So this series is convergent in the entire plane, entire complex plane. So these are really entire functions, actually. But of course, they are non-trivial functions. So you expect anyway that this is going to be divergent at z equal to infinity. Both of these will be divergent at infinity. And then we found that actually the divergence was exponential, actually. So both of these near z equal to infinity, as z goes to, say, infinity along the positive real axis, okay? So z going to, let's say, infinity plus any imaginary part, iy, some finite imaginary part. So the real part I'm taking to plus infinity. In that case, it went like e to the z, right? It was exponentially growing. Okay. This also went like as z goes to infinity plus iy, this goes again like e to the z. So both of them had the same behavior, exponential behavior. But what that meant is that I could find a particular linear combination of these two, which does not go to exponentially, does not, you can cancel the exponential part term, right? So you find that there is a combination which we denote by psi, a, c, z, which was this particular combination. In fact, let me write it down explicitly. So this was given by gamma. This is equation 19.22. Gamma, 1 minus c divided by gamma a minus c plus 1 phi a c z. So this constant times the first solution plus there's another constant gamma c minus 1 divided by gamma a z to the 1 minus c times the second solution. The second solution. 2 minus c comma z. Okay. And this had this coefficients are precisely chosen so that the e to the z terms cancel if z equal to infinity. And so this has, as z goes to infinity, had the behavior simply as z to the minus a. I think, wasn't it z to the minus a? Yeah, z to the minus a. This behaved like z to the minus a. I mean, these estimates were done by this behavior we found by looking at the integral representations for these functions, right? We had this integral representation for this function phi, just like hypergeometric functions had an integral representation, same way these had integral representations, but in terms of Laplace kernels rather than Euler kernels. So, and which we also saw why that Laplace kernel came by starting from this representation and taking this limit. We indeed found that it becomes z minus t to some power, which appears there. That becomes the Laplace kernel in that limit, right? That was one thing we also show. So this had the integral representation, which was phi a c. Yeah, phi a c z was basically 0 to 1 dt e to the zt times t to the a minus 1 and 1 minus t to the power of c minus a minus 1. This was the up to some constant here, which was given by in terms of gamma functions. So that constant is just done to make the at z equal to 0 to make this equal to 1, right? You have this. The normalization was f phi a c 0 was just simply 1. So that normalization fixes this coefficient. You can just put z equal to 0, then this simply is a beta function. So you just divide by that beta function to make it 1. Similarly, psi had the integral representation, which we took it to be from 0 to infinity, or minus infinity to 0, same thing. We took, it's the same integrand, but instead of taking 0 to 1, the one chooses from minus infinity to 0. So that's so this integral is the same, but you take it from minus infinity to 0. And so the way we estimated these behaviors was by just playing with these integrals and seeing, for example, this integral you can write it as an integral from minus infinity to 0, minus infinity to 1 minus infinity to 0, right? And then we estimated these two different integrals. They behave differently. One, this is given in equation 19.17. So in 19.17, you see that you start from this integral and you write basically 0 to 1 integral as the integral from minus infinity to 1 minus infinity to 0, right? And then we saw that whereas this one went like e to the z, okay, this one only had a power behavior. It was only going like z to the minus a, okay. These two integrals split. I mean, in the 19.17, it's written as one. These are, yeah, no, it's correct. It's not 19.17, the one before. There's no number. Just the equation before 19.17, which has no number here. If you look at that integral, which is transformed to 19.17 by a shift of variables, by change of variables, okay. And then you find that the one integral behaves like e to the z, but the other behaves like z to the minus a. Okay. So whenever you have a z whose real part is going to positive infinity, okay, then this will obviously dominate, right? This will be much more than that. The second one, z to the minus a, correct? However, if you suppose you choose not plus infinity but minus infinity, suppose you go along the negative real axis to infinity, okay. In that case, this will be exponentially suppressed, right? So this will be the leading behavior then. The second integral will be the leading behavior. Okay. So this is quite funny because, I mean, this has very different behavior. As you go to z equal to infinity along different directions, you get very different behavior here. Okay. For example, as you go along the positive real axis to infinity, this is going exponentially, blowing up. Whereas if you go in the negative real axis to infinity, minus infinity, then you see that it behaves like z to the minus a. Okay. So it's wildly fluctuating. And that's you expect anyway, because at z equal to infinity, it is an irregular singularity, right? So the solution will have essential singularities. And this is one theorem, I think, which I didn't prove it. I think I didn't prove it. There was a statement about what are the certain behaviors or the essential functions which have essential singularities in the second chapter when we discuss the complex the variables, right? So there was, I mean, the things which had this essential singularity, they were kind of wildly fluctuating near the, as you go near this essential singular point. I mean, essentially you could get any value of the function in any arbitrarily close neighborhood of so that's why, I mean, see, as you go to z equal to infinity along the different direction, which is the same as if you make the coordinate transformation 1 over z going to 1 over z prime, right? So in the z prime coordinate, as you're going to 0, depends on which direction you are coming, you can get completely wild values of the functions. So this is the behavior. Okay, so these were the main points. So now let us see what happens for the, I mean this, yeah, so some of the functions which are related to now this confluent hypergeometric function. The same way as we saw the Jacobi polynomials, I mean Jacobi functions and what is it, Legendre. Legendre is a special case of Jacobi anyway. So basically Jacobi functions are related to hypergeometric functions, right? Jacobi polynomial appears only for a very particular values of a, b, c, right? Otherwise, it would be generally a Jacobi function, not a finite polynomial, but it will be an infinite series. But for some particular values of a, b, c, you know that this series could truncate, because it just happens that the coefficients of all the higher powers just vanish. So therefore, effectively, it becomes a polynomial, right? So we saw that. Now let us consider, say, let's see now what are these confluent hypergeometric functions related to what? What kinds of functions? So in particular, I will just, let me discuss the, briefly I will discuss the Hermite polynomials, I mean Hermite functions, and show the Hermite functions can be expressed in terms of this confluent hypergeometric. And then move on to Bessel functions. So whatever I can say, I will just say today and then stop. Now, of course, obviously, that will not be, I mean, it will be very brief discussion of both the Bessel functions and the Hermite functions. But you are encouraged to, I mean, just go through this during the Christmas break and see. Because this will appear many places, I mean, these functions. I hope Binu is going to give you a big set of problems to do in the Christmas break, because you'll have a lot of time, free time to work on. By the way, what should we do about exam? What is Vinu said that you prefer February, right? What about March? Huh? I mean, the reason is that I think you have now, you're going to have electromagnetism, right? Yes. But that I think will finish by end of February, no? So March will be essentially free, no? You'll have nothing to do. I mean, no course in March. So one could have exam also in March. I mean, that's another possibility. But the danger with that is that there's a more gap. So you might start forgetting these things. Although between February and March, it's not such a big difference. You know what I mean? Okay, we can discuss that. I mean, yeah. But there's a possibility. Either February or March is up to your convenience. Okay, so this is basically the harmonic oscillator problem, right? I mean, Hermite the equation comes from that. And the equation was simply this second order differential equation. I mean, this is in the harmonic oscillator basis. So plus nu plus half minus 1/4 z square is equal to 0, right? That's basically the harmonic oscillator problem. This is the harmonic potential, oscillator potential, which goes like z square or x square. X is now replaced by z, right? Because in the harmonic oscillator problem, x was just a real variable. This was a function of real variable. You have d2 by dx2, right? But now we've just taken the real, from the real line, we have extended to the complex plane. So this became a complex function. No, not complex potential. I mean, you just look at this differential equation, you find the solution as a solution of z, right? But then if you just replace it in the solution z by real part only, then it just gives you the original solution.
But is that the meaning?
No. I mean, no, this is in the, Yeah, I mean, it's like a kind of analytic continuation of the whole thing. I mean, if you have some function on the real line, you just analytically continue everywhere. So it's, but I mean, but it's equivalent. I mean, for a solution with a z being x or z complex, there's a, I mean, one-to-one correspondence between that, right? The advantage with the z, keeping z, is that you can study, because we know a lot about the complex analytic functions, right? I mean, all the second chapter that we discussed, right? There's a huge amount of information we have. So it's always nicer to extend to the complex plane, because then you can ask many questions of issues like monodromy and so on. What happens when you move around the singularities, etc., no? Which you cannot do in the real line. There's no notion of going around the singularity, right? So there are many the nice mathematical properties of these functions you can study by going to the complex plane. No, physical thing, physically you would not have. I mean, in a physical problem you would have real potentials. In fact, if there are imaginary terms, then that would mean kind of decay. It's an unstable system. Decay, yeah. Because Hamiltonian better be Hermitian operator, right? So if you have an imaginary part of the potential, then I mean, Hamiltonian is not Hermitian, which means that the time evolution will not be unitary. Okay, because the time evolution is simply exponential of the I times Hamiltonian, right? So if Hamiltonian is not Hermitian, that will not be unitary. Okay, so what do we do? So how do we map? So the claim is that we can map. I mean, in the third chapter, when we discussed the Hermite polynomials, and we showed the Hermite polynomial satisfies a differential equation, it was not exactly of this form. Okay, it was in the sense that, I mean, the solution of this equation will be e to the power of, okay, that depends on normalization, because the way these numbers appear. I think according to this normalization, it is minus 1/4 z square times the, let's call it hn. If nu was equal to n, and nu is equal to minus n, or sorry, nu equal to minus n. No, so if for nu equal to n, so I just want to relate, I mean, this is not the equation you saw, right, in the third chapter. But that equation is related to this equation by simply do the following. Write this u as e to the minus 1/4 z square times some v, let's say. Okay, then you'll get again a second order differential equation for v. That second order differential equation on the v will be the equation that you have seen in the third chapter. Unfortunately, I didn't bring my third chapter, but yeah. Okay, but let's get it. Let's get this equation. Okay, let's get this equation. So we have to do this thing. So substitute that here. You'll find, so d2u by dz2, you'll have two terms. So e to the power of minus 1/4 z square will come out as a common factor, right? From each term will come out. So there will be one term where both the derivatives hit v, so it's d2v over dz2. Then there will be a term when one derivative hits the exponential factor, other derivative hits there, but there's a combinatoric factor of 2. So you get a plus 2 times the derivative acting on the exponential is simply minus 1/4 times 2z, right? The derivative of that, which is minus 1/4 times 2z. Times derivative acting on v, which is dv by dz. And finally, there will be a term which when both derivatives hit here, okay, and that will be, so what is it? If the two derivatives hit here, d2 by dz2 e to the minus 1/4 z square, well, that's the same as d by dz acting on minus half z e to the minus 1/4 z square, correct? Because this minus half just came because minus 1/4 times 2. And then I have to take one more derivative. So there will be a term which will be simply minus half coming from here. Then again another minus half z from there, so that square, it becomes square of that. So 1/4 z square times e to the minus 1/4 z square, right? So that term then is, so plus 1/4 z square minus half times v. But then I can also combine this part, right? This also is, there's no non-derivative term. So you get here plus nu plus half minus 1/4 z square, okay, v equal to 0. So this exponential is completely outside. So that's the equation you get. So this becomes d2v by dz2 minus z dv by dz. And then here 1/4 z square cancels with that, minus half cancels with that. So very simple, plus nu v. This is the equation. This is equal to 0. Right? And I think if probably you should see that when nu is equal to n, that is the equation that you had seen in the third chapter. That's satisfied by Hermite polynomials. So what would happen is that what we'll consider for general nu, and again what should happen is that when nu is a positive integer, then this solution truncates, the series truncates to a finite number. Right? That's what should happen. But now still, I mean, what has this equation got to do with the confluent hypergeometric equation? It's not obvious, right? Because remember, confluent hypergeometric equation was given in terms of, it was like this, z d2 by dz2 plus c minus z d by dz minus a, right? This acting on something equal to 0, right? This is what, but that doesn't look like that equation, right? So you can actually map it to this equation by, let's define a variable t equal to z squared by 2. And let's rewrite all of this equation in terms of t. So, right? So instead of z, we write it in terms of t. So what is that? So d by dz is obviously dt by dz, d by dt. Yes? Now dt by dz is just z, right? So this is simply z d by dt. So now if I apply two derivatives, d2 by dz2 is the same as d by dz acting on z d by dt, right? So there will be two terms, one d by dz hits there, so that just gives me d by dt, and the other one will be plus z, then d by dz acting on d by dt, but that the d by dz I use the fact that it is z d by dt, so you get here z square d square by dt square. Now z square is 2t, so I can as well write it as 2t. So that's the equation. So let's substitute. So you get here from the first term you get 2t d2 by dt2, okay, plus d by dt. That's from the first term. From the second term, okay, dv by dz is already z d by dt, but I have another z there that makes it z square, and z square is 2t, right? So it's minus 2t dv by d by dt. Okay, I can put here v, and then it's simply that plus nu. Now it looks like the hypergeometric. You see, let's just divide by 2, by 2. So this goes out. There's a half here. This goes out, and there's a half here. Okay. So we see that this equation is the same as the, okay, instead of z, you just write in terms of t, right? So this equation. Okay. So it's the same equation except, so the particular value of c and a, c is equal to half, and a is equal to minus nu by 2. Okay. So therefore we can express Hermite functions or solutions of the original equation in terms of the solutions we already know of the hypergeometric, confluent hypergeometric. So the solution is phi. I mean, there will be two solutions again. Phi. Phi. So the phi of c equal to half. A. So minus nu by 2, half, and t. But t is z square by 2. So z square by 2. So that's the solution. minus nu by 2. Yeah, so this is the solution. So I mean, yeah, in fact, let me see if they have used the symbol. If I see, they have used the symbol. So the solution here, so going back to this one, let's call this solution as d nu. D nu. Nu, it depends on the nu. There's only one parameter here, nu. So it will be, the solution will be some d nu of z, but then you see that d nu of z, I mean, in order to go to this confluent hypergeometric equation, I have to first replace u by that, right? So the d nu is the e to the minus 1/4 z square times v, where v is given by that. So going back to this thing, finally we will conclude that d nu z is simply e to the minus 1/4 z square times phi minus nu by 2, 1/2 z square by 2. Sorry, phi, in fact, there are several possibilities. I could just choose phi or psi. In fact, it turns out it's a psi. It's a psi that we need to look at. The one which collapses when nu equal to integer, the one which collapses to Harmonic polynomials is the, I mean, there'll be two solutions, right? One we call phi, another we call psi, right? They have different behaviors at infinity. So the one, so there will be phi solution as well as psi. There will be two solutions, minus nu by 2 half z square by 2, and so the one which becomes the Hermite polynomial when you choose nu equal to n is the psi solution. Okay. Now I will, okay, how do you prove this? The thing is that for the psi, you see, I mean, now can I erase all this part here? I mean, try to do this. I think, I haven't checked it, but I think it should be possible to check this computation. So the idea here is that, I mean, you have to use the psi. So psi had this integral representation, which was, well, either minus infinity to 0 or 0 to infinity by change of variable. It was 1 over gamma a, e to the, t to the a minus 1, and 1 plus t to the c minus a minus 1. I mean, previously I wrote it as minus infinity to 0, but that was with a 1 minus t, right? Now you just take t to minus t. So then this becomes 1 plus t, and the integral becomes 0 to infinity dt. T to the power of z minus, sorry, not c, z minus a minus 1. Is that no c? No, what is the times the exponent, the Laplace, right? E to the tz. So c minus a minus 1 and e to the tz. E to the minus zt. Okay. Because before it was plus zt, but I have to change the variable t to minus t to make it e to the minus zt. So that's the integral. Okay. But for this integral to make sense, remember we had to impose a condition that let me see, what was the condition? The real a is positive or something like that, right? I think. Sorry? I mean, well, I mean, for this integral, you see that you have to have the only possibility is a singularity here, right? I mean, let's suppose the real z is positive. Suppose real z is positive. Then at t goes to infinity is exponentially suppressed. So there's no problem with this. However, there is a problem at the origin, right? So for the origin, I mean at t equal to 0, this would be fine if real a is positive, right? If real A, for example, was equal to 0, then there is a 1 over t here. I mean, if say A is 0, then it's 1 over t. And dt by t will have a logarithmic similarity. If A is negative, it's even worse, right? So the condition was that real A should be positive. In that case, there will be no singularity at t equal to 0. So this integral will be well defined. However, if you want to study what happens when nu equal to n, because that was the, from the harmonic oscillator, remember the nu was quantized. Nu had to be n, integer, right? Positive integer. But here, this is the A. A is minus nu by 2. So if nu is a positive, nu is a positive integer, A is negative, right? So then this integral you cannot use. This is not well defined, right? So you should use some other expression for the psi, which makes sense. And the expression that you can use is just this relation that we found before. I mean, we found that this was a linear combination of the two terms, A, C, Z. Was equal to gamma 1 minus c over gamma a minus c plus 1 phi a c z, and then plus gamma c minus 1 over gamma a. I mean, this equation 19.22, z to the 1 minus c phi a minus c plus 1 2 minus c z. So use this expression, and for each of the phi, we have series expansions, right? We already have the series expansions in, where is it, in equation? Yeah, in equation 19.1, no, not that, where is it? Yeah, it's 19.10, right? So in 19.10, we have series solutions for the phi. Okay, that is, I mean, so phi ACZ was the sum gamma c over gamma a summed of gamma a plus n over gamma c plus n times gamma n plus 1 z to the n. Okay. So same expression like this, just replace AC by these quantities. So you get this series expansions, and you should be able to show that when A becomes minus n by 2, okay, this should truncate. This should truncate to only a finite polynomial. Okay, so that's the idea. I mean, please check it. I mean, I haven't checked it myself, but I think you try to check it and see if you can find that. So, so then if that happens, I mean, if that happens, that you see that this truncates to some, yeah. There's some minus e to the some pi factors, yeah, probably there is something because yeah, you have to change. But let me see if should be put there. No, yeah, but I think that so finally the expression is defined in terms of directly from 0 to infinity, because true. I mean, if you look at the equation, the original equation which was given in 19.14, okay. So in 19.14, the integral was written as minus infinity to 0, right? But it is in the front, there's a constant, okay? Now, what one is doing is that one is saying that you absorb that, you are saying that it is extra minus to 1, minus to some power, minus 1 to a minus 1 or something like that, right? That is absorbed in that constant, too. Because here it was just a constant. I mean, that equation was basically saying that u is proportional to this, okay? So you take this as a definition of the psi. Take this as a definition of psi, which is related to that thing. When you transform to minus infinity to 0, there will be some extra phase there. Yeah, correct. Okay. So I mean, please check this. It should be. I mean, I don't know. Try to do that. Huh? Just plug these expansions here, and combine them again to see what are the behaviors any, z to the n powers, and you should be able to show that this is, so first of all you have to replace this z by z square, because the argument is z square by 2, right? We are looking at the psi with this is this a, c, and this is z square by 2. So you should replace this z by z square by 2. And then collect all the terms here, and you should be able to show that when mu is equal to n, right, this series must truncate. So it should truncate at up to z to the n. Beyond z to the n, say z to the n plus 1 and so on and so forth, should vanish. So try to check that. And if you can show that, then that is exactly, that tells you that the Hermite polynomials you wrote down, Hn, right? Hn is nothing else but this psi up to some probably a constant factors. Okay, the normalization, it seems, okay, it turns out the following relation. Hn of z over root 2 is in fact 2 to the n psi of minus n by 2, 1/2 z squared by 2. Okay. So this, please check, to check this, what you need to show is that this truncates, right? And then that's, okay. These 2 to the n and root 2, etc., these are just various normalization factors, so that's not the important point. But the important thing is to check that it truncates to n. So another thing, so this was the Hermite. Let me quickly also just for Laguerre also, this is something again you should try to check, that the statement here is that Laguerre, please check this again. Again, it's a similar method again. Just start from the Laguerre equation which defines Laguerre polynomials, right? The differential equation the Laguerre polynomials satisfy, and then show that that equation is related to the confluent hypergeometric equation, and you will find that this Laguerre, this is given by this equation L, the last equation on that page, 321. So which is L mu n times equal to unfortunately, I didn't bring the third chapter which had the Laguerre equation. Then you should look at stare at the Laguerre equation and stare at the confluent hypergeometric, and then see if you need to change some variables or something, right? And then so that you can map from one to other. I think it should be a straightforward map, because this, you see, this is a direct relation. Up to a constant, L is simply proportional to phi. Okay, so that means the equation must be more or less the same equation, up to some normalization factors. So minus n mu plus 1 z. So this, so you should be able to show. Do you have the Laguerre equation somewhere? I don't. In fact, it's exactly the confluent hypergeometry equation, right? Because the second derivative term comes with the x. This is. Let me write down Laguerre equation, which is exactly identical. So therefore, you don't have to do any work. Unlike Hermite polynomials where you have to make some transformation of variables and so on, here it's directly. So Laguerre equation is x d2 by dx2 L n nu x, okay, this is a function of x, plus nu plus 1 minus x d by dx L mu n plus n L mu n equal to 0. So this is directly the confluent hypergeometry equation, where you just have C equal to nu plus 1 and A equal to minus n, right? So this is directly there. Yeah. So again, the point here then would be to show that, so indeed you see that, so here I wrote mu. Okay, let me put here nu. Nu is here. because there was a one parameter family, right? Remember that because you had a choice of the weight functions and the, you know, so when you solve for the weight functions, you have one parameter family there. Unlike in Jacobi case, there were two parameter family. In Laguerre case, there was only one parameter. There was that. So, so here it will be in general the solutions. The general solution of this equation, I mean, of this equation will be simply a linear combination of this, right? I mean, because this is the value of A, that's the value of C. Huh? So the general solution will be this plus psi, the second solution psi. The two linearly independent. Choose any two linearly independent. The point again will be to show that when you choose n, this A equal to minus n, this phi truncates, no, to n. So then you get a finite polynomial. So these two things, please try to check that. Okay. What else are related to? There's a. I mean, there's another function which sometimes enters. I mean, particularly in statistical mechanics, it might enter. It's called something called error function. Okay. So the idea is, I mean, you have, say, some probability distribution. Let's say there's some Gaussian distribution, right? But now you want to ask, okay, the total integral is 1. You have normalized to 1 because total probability should be 1, right? Okay. But say you want to see, okay, what is the probability that says the object is within some range? Right. Of course, if you say if I include add up the probability of particle being anywhere, then of course total probability is 1, right? But I want to ask more refined question. What is the probability that it is in some interval, right? That means I have to integrate the Gaussian in a finite interval. Okay. So that is what's called the error function. Okay. So it gives you the probability that something is inside some interval. I mean, so it appears as a natural thing which appears in statistical mechanics, probability theory and so on. So that function is just simply defined by, you take, this is called error function. It's usually denoted, written as ER. No. Okay, I don't know, error function. Error function. And let's define it again as a function of Z. This is simply the integral e to the minus t square dt. So this is a Gaussian, you see. But you want to ask what is 0 to, let's call it x, 0 to x. Or just think of z, it doesn't matter. Just think of z. Okay. So it's like, so the picture is here. This Gaussian is going to be a peak at t equal to 0, right? And it's exponentially suppressed far away. So this is the kind of peak, right? This is the thing. And you want to ask, for example, what happens, what is the probability that something is in between this range, right? So that will be from, say, minus x to plus x, but this is an even function, so the same as twice 0 to x integral. So these integrals will appear there. Okay, so how is that related to this thing? Well, it turns out that this is the same as z. So this is the same as z. We can check it. We can check this. Phi 1/2, 3/2 minus z square. Okay. This is where, remember, what was the phi? Phi had this integral representation. Phi AC z was the integral representation e to the tz. I think the integral was from 0 to 1, and t to the power of, what was it? T to the a minus 1, and 1 minus t to the c minus a minus c minus, yeah, dt. Okay, with some prefactor, I don't know. Yeah, there were some prefactors, right? Gamma of something. That was to normalize it to 1. So it was, yeah, gamma c divided by gamma a, gamma c minus a. That was the integral? Yeah, correct. Yeah, it's in 19.12. So if I now take, so let's see, this was, we'll see. This is in fact perfectly okay, because you see this integral was defined for real C greater than real A greater than 0, right? That was the condition. But this is perfectly fine. A is half and C is 3/2, so this condition is satisfied. So this integral will perfectly make sense. So now to see why this is the same as that, you just have to change the variable. Let's substitute, for example, C and A. So when it's A is equal to half, so this integral is the same as, okay, gamma C, so gamma 3/2. Okay, these are numbers. I'm not so interested in that, but A is 1/2, so gamma 1/2. And then C minus A is 1, gamma 1 is 1. Okay, so that's that. And also even that, you see, the gamma 3/2 is half times gamma half. So this cancels and you just get a 1/2 here. All the prefactor is simply half for that. And then the integral here is 0 to 1 and e to the tz. Yeah, so a minus 1, so 1 over root t. And c minus a minus 1, that is 0. 3/2 minus half minus 1. So there is no 1 minus t, right? So it's a very simple integral. You see? Okay. Now to compare with that, just to take t equal to t prime square. Z is minus z square. Minus z square. Good. Yeah. Okay. So now take t equal to t prime square, right? So you get here 2 t prime dt prime. Root t is t prime. And then here you get e to the minus t prime square z square. And then there's a half, 0 to 1. So there's 2 cancels. Okay. T prime cancels. So now it's just a Gaussian, except that here it was just a t. There is a t prime square z square. I mean, here is only t square. Here is t prime square z square. So then change again, call t prime equal to t double prime over z. Okay. So then this becomes e to the minus t double prime square, and then dt prime becomes dt double prime, and 1 over z comes out, because anyway that's outside the integral. But the range becomes, see, when t prime is 0, t double prime is 0. But when t prime is 1, t double prime is z. Yeah. So that's exactly that integral. So it's a, yeah, there's a z also there outside. Yeah. So you see that 1 over z cancels with this z and you get. Okay, so that's just to show how a lot of functions are related to this our Confluent. Finally, let me just discuss briefly. Oh, it's 11. Oh, so very little time. Just the starting point of the Bessel functions. Okay. Any question? I mean, up to this point. No. Okay. So Bessel. So Bessel equation. Bessel equation is d2 u by dz2 plus 1 over z du by dz and plus 1 minus mu square over z square u equal to 0. That's the Bessel function. By Bessel equation. Okay. Now this again, this equation can be mapped to a confluent hypergeometric equation in the following way. You change the variable. You write u is equal to z to the nu. I mean, so this has you see is a regular singular point at z equal to 0. This p has a first order pole, q has a second order pole, which is fine. This is regular singular point. So z to the nu, and then e to the minus iz, yeah, times say v of z. So if you write it like this and substitute, so what we will get, there will be several terms. Hopefully we'll find that this is a hypergeometric, confluent hypergeometric equation. Okay, so we have to just substitute this. So two derivatives. So there will be, and then after taking, you take these factors out. So you will get d2v over dz2 plus 2 times the derivative of that times derivative of that. So this derivative of that gives you nu over z, because I'm taking out z to the nu outside, e to the minus iz outside, right? So there will be one term which is derivative hitting there will give you nu times z to the nu minus 1, but since I take out z to the nu, there's a 1 over z, and then minus I, that's it, right? From here, okay, that times dv by dz, and now plus this, so plus 1 over z, this is 1 over z. So z, so there will be two terms again. So one is simply dv by dz, and the second term would be plus nu over z times v, and then minus I v. That is from, I forgot also, this was the first derivative term. Already for the second derivative, there's also a term and both derivatives hit here, right? So that will come with, there will be a term which will be, so again you have to decompose. So there's a nu times nu minus 1 over z square when both derivatives hit here, right? When both derivatives hit here, you get a minus 1, right? And when one derivative hitting here, one derivative hitting there is 2 nu over z, and then there is a minus I, so minus 2I nu. This all is multiplying v. And finally the last term, which is simply 1 minus nu square over z square times v. Okay. So this is the what the differential equation becomes. Now let's see what happens. So dv by dz. So if I combine dv by dz, so this becomes 2 nu plus 1 minus 2i. Yeah, that's one thing. Now the crucial point is that for the confluent, you see, for the confluent was very similar to this, except there was no second order pole, right? So let's see the second order pole cancelled. The reason for this thing is presumably to cancel the second order pole. So is it true? Let's look at the 1 over z square term. So 1 over z square term comes from, for example, this product. So there is a nu over z square, so 1 over z square. 1 over z square v, that's what we are looking at, right? So from this term there is a nu, from this term. From here you get plus nu times nu minus 1, right? And from here you get minus nu square, which is indeed 0, right? So 1 over z square term cancels. So then it's going to be of the confluent. No, still we need to also look at a 1 over z term. No, the confluent hypergeometric was z was here, there was a linear function of z here, and here it was a constant. Okay, so that means once you divide by z, this should be just a first order pole, no constant term, right? So let's see the constant term. The v, this is the first order pole. In fact, yeah, there is. Yeah, it is minus 1 and plus 1, right? This v. So this cancels with that. So that is the reason. You see, that's the reason for that. This minus 1 it came from there. You see, because I had to take two derivatives, and that's why the imaginary I, because if it was if I was not there, it would be plus 1, right? And that would have added up. So the reason for this I is precisely to get a minus 1, and that cancels. So now it's going to be confluent hypergeometric, and just write down the final equation. It's so it's say z times d2 v. I just multiply by z. Okay, and then here you get 2. The 1 over z is coming with 2 nu plus 1, right? So plus 2 nu plus 1, and then minus I z, huh? Minus 2I z. Correct? I mean this minus 2I, but I'm multiplying by z. So all that is multiplying dv by dz. And then there is a 1 over z term with v that comes, so that z, multiplying z, that disappears. So you get here minus I from there. From here you get minus 2I nu. That's it, right? Yeah. So, okay. So I can write, so minus I times, again, 2 nu plus 1. Huh? 2 nu plus 1. V. That's equal to 0. So this is the hypergeometric question. And let me see if, to identify it exactly, I should be able to absorb this I. So this one. Yeah, I can absorb. So let me divide by I everywhere. In fact, let me divide by, I. First, let's divide by I. So there's a I here, there is a 1 over I here, and this I goes out. And let's now call Z Z equal to minus IT. Okay. So then I can absorb, or in other words, T equal to IZ. Huh? T equal to IZ. Then this is as T, that is d by dt. Okay. And this I can write it as I squared I. IZ is T, and I squared dz square is dt square. So this equation in terms of T variable becomes simply T d2 by dt2 v plus 2 nu plus 1 minus 2. So better also do 2. Let's put also 2 here. Right, it is 2. 2iz is equal to 2. So you get rid of this 2. So how shall I do? So I think I should divide this entire equation by 2 probably. This one. I mean, okay, let's just do it in 2 steps. So that's that, minus 2t dv by dt minus 2 nu plus 1 t v. That's equal to 0. Now I want to write t as, divide this equation by 2 first of all. Okay, so there is this here, there is this here, and there is this here. Okay. And now call 2t as some t prime. Okay. So 2t as t prime. So this will not change because this is a numerator and denominator. There is a t, so this will not change. But this 2 will be absorbed because 2t is not t prime. Okay. Similarly, here again I can write it as 2 square 2. So 2t is t prime and 2 square. This is t prime square. So if I write 2t is equal to t prime, that this equation becomes this equation of the confluent. I mean, these are just to keep track of what should be the argument of the so 2 nu plus nu plus half from here minus not nu plus half, so 2 nu, so because this 2 is absorbed there, so 2 nu plus 1 minus t prime dv by dt prime, and then finally last one minus nu plus half v equal to 0. Okay, so this shows us that in this equation C is 2 nu plus 1 and A is nu plus half. Okay. And the argument, so what we are seeing is that the solution of this equation, solution of the V, so V is of the form, so V should be given as a solution of this equation. So for example, one of the solution is phi of A is nu plus half, C is 2 nu plus 1, and T prime right? But t prime is 2t and t is iz, so this is 2iz. Argument is 2iz. And so general solution will be this plus the second solution. Let's say, I mean, either you can choose the psi or the second, whatever. The two solutions there are. Is that, okay, I don't know. The second solution is psi. Plus half. So you can just, express the general solution as that. The one solution, so going back to this expression, going back to the original thing, because we had to, the original solution of that equation was this times v, right? So the one, this is called the Bessel function of the first kind. Huh? So Bessel function of the first kind is simply just take this term. So it is denoted by j nu of z. I mean, it's all, yeah, it's, okay, there's some normalization. This is up to you to decide, but okay, standard normalization. And so there is a z to the power of nu, but again, this is part of the, I call it z over 2 to the nu. This 2 to the nu and gamma nu plus 1 is just, because any constant, I just choose alpha equal to that. Okay. And then you have e to the minus iz from here, okay, times this phi. Okay. So this is called the Bessel function of the first kind. And you can get the Bessel function of the second kind, etc., by choosing the second solution. Either use, two linearly independent solutions. Either you choose a psi or you choose the second one, which goes like z to the 1 minus c times phi of the different arguments, right? You can choose either of them. I think the second one is used for the second solution. Not the psi, but the other one, the phi. I mean, there was another solution which was z to the 1 minus c for phi. What was it? A minus c or something. I forgot now. Anyway, there was some second solution, right? A minus c plus 1, 2 minus c, z. Well, z was, okay, t prime. So that will be another solution. So t prime to the 1 minus c, where you substitute c, value of a and c. This is the value of a and that is c. Okay. That will be another solution. So either you use this or that. It doesn't. But the standard terminology is that this is the Bessel function of the first kind, and Bessel function of the second kind, I think, is using this one. Anyway, there are two linear independent solutions. You can choose your basis. Okay, now it turns out you can, after this must require probably a lot of work, but you can expand all of these things. This is analytic near z equal to 0. So and we know what the power series expansion of the phi is, right? That was given earlier. Last time we obtained the series solution for that. This one is again exponential, so you can expand it near z equal to 0. Again, it will be series. But when you combine all this and regroup, so there's a series here, there's a series here. So you take the product of the series, no? So it must require some work. But at the end of the day, they find that this whole thing, I mean, it should be possible to find that this whole thing is z over 2 to the nu, because this part is there in the beginning, in the front, and all that should give you an analytic function near z equal to 0, which means it has a series solution, and it turns out to be given by 20.6. I will not write it down. I mean, 20.6. Okay, let's write minus 1 to the m and factorial m gamma of m plus nu plus 1 times z over 2 to the 2m. Okay. I mean, it should be pretty, it should require some work, I think. It cannot be so straightforward, right? Because here you have to take the product of the two series. So that should require some identities involving gamma functions to prove that. I mean, so if I want to look at z to the 2m, you have a sum of terms, right? You can take z to the 2m from here and 1 from there, or z to the 2m minus 1 from here, z, you know, all the way up to z to the 0 from here and z to the 2m from there. So there are 2m plus 1 terms. You have to add them up, right? So it must be pretty non-trivial, but I mean, eventually that's what turns out to be this coefficient. Okay, I mean, I think one can just keep, yeah. No, maybe I should just stop at this, because there's a lot of stuff here in the Bessel functions. But either you do all of it, which will require maybe several lectures, no, or else I don't see the point now. I think you can just maybe stop here and.